So the premise for this problem is that in the clean room here, I think you guys have probably used it. It's a useful little system. There's this Filmetrics interferometer that can use light interference as a function of wavelength to determine the thickness of different film layers in a multi-layer structure. So that could be used to determine photoresist thickness or really any other film thickness that you deposit, other than, a thick metal won't work. But so the premise of the problem is it tells us that we've got 1 micron of this PMGI photoresist on top of a silicon wafer, and we're going to use a constant refractive index for the PMGI photoresist. And we download from the Filmetrics website. They have this nice database of refractive index, so we can download the refractive index of silicon as a function of wavelength. And the idea is kind of like I've drawn here, is you have this incoming light ray coming from the machine, and it's going to be white light, so all different wavelengths, but let's just say we have incoming light ray, and it's going to transfer from one medium into the other. In this case, it would be from air into the photoresist. And when that happens, of course, some of the light is transmitted and some of the light is reflected. And then the same thing happens when the light transfers from the photoresist to the silicon. Some is transmitted and some is reflected. And what the machine does is it measures the total intensity of this reflected light, and it is able to work out from that the photoresist thickness. So what we're going to do is just to try to calculate this, the intensity of the total reflected light. And you could imagine that if I just had one transition from air into photoresist, this is probably pretty easy to do, just using Maxwell's laws. But when you have this multi-layer structure, some complicated things start happening, because you could see that you get reflection from the photoresist silicon interface, and then that bounces upward. But actually what should happen that I didn't draw here because I wanted to keep my picture neat is the light then hits this air photoresist boundary again. So some of it gets reflected off of that, and some of it gets transmitted, and then it hits this boundary again and reflected, and so you kind of have this never-ending cycle of reflected and transmitted light. And so trying to add up by hand all the different components, you could maybe do some really extensive series and get pretty close, but that sounds really tricky. So there's a different way of doing this, and that method is called the transfer matrix method. That's what I'll be explaining today, is how to do that. So the idea is, of course, we're going to represent the light as this electromagnetic wave. And so in any region, we can represent the light, where Z is, kind of through the depth of our sample. So I drew it wrong here. This shows, incidence at an angle, but we're going to do it for normal incidence. You could solve this for incidence at an angle, but I think it gets a little bit trickier. But so Z is going to be our depth through the sample, and in any region at any point Z, we're going to have some right-going wave and some left-going wave. Right? So we can represent the light as just the sum of these two plane waves. And then based on the fact that the magnetic field at any point is going to be related to the derivative of the electric field, and also related by this constant, the characteristic impedance, then we can represent the magnetic field kind of as shown here. And the idea is you'll notice that E sub r and E sub l are appearing in both. And there's also these exponentials, that are kind of in both. Obviously a minus sign here. But what you can show is that this matrix M allows you to do this. It allows you to calculate based on the electric field and magnetic field at some point Z, their values at some point Z plus L, assuming they're moving through a uniform medium. And you can do this by, if you represent this cosine and these signs as sum of exponents, then you can show that, if I take the product of M with these two values, I do in fact get this, where, this Z here is going to switch to a Z plus L. So I encourage you, it shouldn't take too long to do that, but you can show that this product using this definition for M does in fact give you E to the Z plus L and H to the Z plus L, using these definitions for E and H. And this is all, I'm taking all these equations from just a Wikipedia article on the transfer matrix method. So I encourage, because M allows us to calculate how Z and H propagate to some point, E and H propagate to some point Z to their values at Z plus L, what we can show is that the total propagation of the electric and magnetic fields through a multi-layered structure is can be represented through the product of multiple transfer matrices. So if I have a multi-layer structure with n different layers, then the total transfer matrix, which would take E and H to some point E and H through the entirety of the multi-layer structure, I just take the matrix product of multiple transfer matrices and find kind of this total transfer matrix that's going to allow me to, if I knew E and H on one side of the multi-layer structure, calculate E and H on the other side. So that's what we're going to do here is use those transfer matrices and calculate one for each layer in the structure. But you also need a little bit more information. And one is, we're going to start with some representation of the electric field on the left side of the multi-layer structure. So we're going to say that we have this multi-layer structure where there's kind of an air, photoresist, silicon, air sample here. And what I'm going to say is the electric field on the left side is some right-going wave, where KL is just the wave number in air in this case, in the left medium. And there's some right-going wave heading into the sample of some amplitude E naught, right? So this is like the initial amplitude of the electric field for the incoming light. But there's also some left-going component of the wave where its amplitude has this cofactor, which we're going to call the amplitude reflectance, R. So if much of the light is reflected, like if this is a mirror, then R is going to be almost 1, right? Because the reflected amplitude is going to be almost equal to the incident amplitude. But if this is like pretty much just completely transparent, then R would be close to 0. Okay, and so we can represent the total left-going wave, kind of the sum of all these different reflected components, by this term here. On the other side, on the right side of my whole multi-layer structure, I'm going to try and represent the electric field, but there's one important difference, which is, first off, there's only a right-going wave. There is nothing to reflect off of here, so there's nothing to make a left-going wave. So that's a simplification. And then the total amplitude of the right-going wave here is equal to E naught times some cofactor T, which we're going to call the amplitude transmittance, which is going to just represent the amplitude of the wave that actually passed through the entire multi-layer structure. Okay, so these kind of are our two important parameters that either if we wanted to know the total transmittance or the total reflectance, these are going to be the parameters that we need to find out, T and R. Okay, so the strategy is going to be we have this representation for our electric field to the left, our representation for the electric field to the right, and we know how to calculate the transfer matrix, and I'll say a little bit more about this later, but the transfer matrix for each layer. So in our case, we have the photoresist layer and the silicon layer. And we know how to calculate the transfer matrix for those. So we could kind of perform the whole calculation now. So the strategy is going to be, so when Z equals 0, that's like right on the air photoresist interface, we're going to represent the electric field as such, where we have a left-going and a right-going component. So this is kind of right when you're transferring from the air into the photoresist. On the right, when you exit the silicon into the air on the other side, this is how we're going to represent the electric field of our wave. And you can see that there's a KL, which is the wave vector in the air on the left, and a KR, which is the wave vector in the air on the right. Air on both sides. So actually, in our case, those Ks are going to be the same because you exit the silicon and you should have the same wave number upon exiting as you did before entering. Okay, so this equation represents where M is the total transfer matrix. This is going to get us from E0 to EZR. And we know that there's this cofactor R and this cofactor T here. So based on this matrix equation, it can be solved using these equations for EL0 and R, ZR, here and here, these can be solved to find the amplitude transmittance and the amplitude reflectance in terms of KL, KR, and the elements of the M matrix. And then, the reflected intensity reflectance, which is actually what we want. We don't want the amplitude. We go kind of like the total energy of the reflected wave, which is going to be related to the intensity reflectance, and the intensity transmittance can be found once you find these amplitudes by just taking the square of the amplitude. So this is the quantity we want in our case, is R as a function of wave number or wavelength. Okay, so the only other trick is finding the transfer matrix using the index of refraction data that we have for silicon, and again for the photoresist we're just using a constant index of refraction of 1.6. So you'll see that technically the magnetic field is related to the electric field by this derivative with these cofactors, where this is the characteristic impedance, which is related to the index of refraction. But the only requirement actually in this method is that you across the transfer of one layer to another, that the derivative of the magnetic field and its value across the interface is constant. So we don't actually have to work with the magnetic field. Because the magnetic field is related to dE dZ, we can just work with dE dZ across the interface. And so, whereas we originally wrote our transfer matrix like this, we can actually calculate it. Notice that I'm switching here from IZC to just 1 over K prime, where K prime is the wave number in the medium with the index of refraction, and that's basically what you're doing here. Is you're just multiplying this by this prefactor in front. You'll notice that gives you a 1 over K here, and if you do that over here, it gives you a minus K prime here, or minus K. We're switching between K and P prime here. But anyways, this is what we're actually going to use to do the calculation. We're going to find the transfer matrix for each layer using the wave number in that layer, the thickness of that layer, and the wave number is related to the index of refraction. And we should point out that the index of refraction is a complex quantity. There's an imaginary component to the index of refraction which kind of encapsulates the attenuation that's present in that material at that wavelength. So N here is your index of refraction. Just to reiterate, this is a wavelength dependent quantity, and it is also a complex quantity. But based on this, we can find the transfer matrix for each layer, and once we have the transfer matrix for each layer, we can find the total transfer matrix, and then based on these equations, we can find the total intensity reflectance. So I went ahead and did that. There's this handy dandy reflectance calculator. This is like using the same type of calculation that the Filmetrics tool uses in real life. And so I created on their tool the stack that we have with the silicon, the what do you call it? The photoresist and the air on top. And you can download their data. And what I did is I used my own transfer matrix method that I'm calling the plot of this work here, and I plotted mine versus theirs. It fits pretty good. I mean, you can see there's some slight differences. And also what happens here is for some reason their data that they're giving us for the refractive index of silicon, it just kind of cuts out at a value around 820 nanometers, and it lists the value of the refractive index as 0 for all values past that. So you can see obviously my calculation breaks because the numbers I'm using from Filmetrics stop at that point.